We've spoken on about topography, so let's move on to topology. Topology is another word that we have borrowed from mathematics and misused somewhat, but it examines the relationship between different objects. So we can look at whether something is inside some other object, contains, whether it's outside, whether they don't have any area of intersection. Overlapping, where there's a partial containment, whether one object is slightly within inside another but slightly outside of it as well, or just the idea of touching, where they're against each other. So we can illustrate those quite simply with these. We have inside, outside, the overlap here, and just touching these two objects. And of course, in this example, or these examples that we've got here on the screen, these would appear to be perhaps polygons, but we could be talking about polygons and points, polygons and lines. We can combine these in different ways, even points and lines perhaps with touching, for example. Within topology we also have other concepts that are employed in, for example, network analysis and the connections between objects, and this works regardless of the absolute distances between nodes in a network. We're just simply interested in the connections between them. There may be weighting along these connections to give them some form of distance, as it were, although it's not always an actual distance. But all we're considering here are the connections between them. Their actual locations are not the primary information. Another use of the term topology in GIS is to examine digitizing errors. So if we have, for example, here two polygons that should meet nicely, there seems to be some sort of overlap there. That's not ideal. Here they've both got the right form perhaps, but they're not meeting, they're not intersecting nicely. Whereas here, the two forms go into each other, there's no overlap, there's no gap between them, they intersect properly. So this is correct topology. This could be correct topology. This isn't necessarily wrong, but when we want these two objects to actually meet against each other with no overlap, it should look like this. Again, these two objects meet, but their form is incorrect. There's this overlap between them. This does not work well. So this, we're saying, is the good example. Alternatively, again related more to network analysis perhaps, we have some lines consisting of connections between different nodes, and these should meet but don't quite. These cross each other, but there's no connection between them essentially, so that's not correct. What we want actually for our network is something that looks more like this. So this comes in and they meet nicely at this node here, and then this line comes in and meets at this node here. There's a connection between this to this to this. That is topology, correction of digitizing errors in our network here. Doesn't necessarily have to be a network, but it's a similar concept. Going back to this idea of the things that exist within or outside of objects where they share space, and the topology, and which parts are correctly positioned. So both topology errors and the topological connections between things. These are similar, very similar, in fact, to concepts from both set theory and logic. So we can look at things like union of two things. The union of A and B would be all of these objects. The intersect would be just those that exist in this intersect of A and B, where it is both A and B. And then we have something to say like the relative complement of B in A, which is those that are in A but not in B. So that we can just simply translate into a more GIS wording. All points either in polygon A or polygon B. We don't mind either which, because that's "or" in there. All points belonging to both polygons A and B. Yeah, it's just A and B. All points that are only in polygon A. So we're somewhere along we're using our logical terms here to define these as belonging to particular polygons or objects. So let's continue with our analysis of vector data. We've looked at this before. in the vector lecture, but just run over it once again. The spatial join. So we have a table of data here, vector data here, and a table of vector data there. And each row in this table connects to a spatial object here, in this case polygons. And then we have these points here, and these connect to a row in this table. Each point belongs to a row in this table here. So we have information about each of these objects, attributes stored in the tables. There's no common key between them. Even though we have these numbers here, we're saying that this is not the same thing as this ID. There's no common key. But what they do have is this spatial connection. We can see that we can join them spatially because 1 is within 107, 2 is within 106, and so on. So we can connect them spatially. We see that that is in there. That these points can inherit qualities, or these polygons could inherit qualities from the points. Either way, we decide which way that information goes, but we can join them spatially, and we end up potentially with this set, where we have a set of points that have inherited data from these polygons, in this case, where number 5, because it was outside of any polygon, didn't inherit anything. So it's empty here. Whereas all of these other points have inherited data from the polygons. This row could be left out, depending on how you want to run your analysis. If you're only interested in those points that are within, then this can be dropped, or you can maintain it, but with a no data entry in each of these, or empty. Another common analysis for vector is the buffer. So here we have a point, here we have a line, and here we have a polygon, and we're going to buffer them out. Buffering always results in a polygon. So we buffer out like this, say they're buffered twice out here now, to a certain distance. This can be quite handy for working out what other objects are within a particular range of, say, a city or a road or a lake, for example. What objects are contained within its sphere of influence, as it were. So this is the buffer. And how is the buffer created? How does this work? Just do a little bit of maths. It's not terribly difficult. Lots of symbols here, but if we have an object that we want to buffer around, every polygon is essentially a line that goes round back to itself, and we define a containing area. So we're interested in lines. We're interested in forming another line at a particular distance from a point, for example, or the other way round. Now we can define a line between two nodes. A straight line between two nodes has a very simple formula: y equals kx plus m. You may have seen this with other letters, but for now let's just use these. This is a form. This can also be written in another form. You will find this in the literature as well. I'm bringing this in because we will need it down here for working out this distance. We could just use the same letters, but you quite often see the equation written in this form. So let's just, what does this mean? How do these two relate? Well, I've written it here as well. So we can see that this is exactly the same thing. We just shifted the y over to this side, which leaves us empty here, leaving us a 0. And then we can just rename the k to a, and then the b there just becomes 1y, negative 1y, because y is unchanged. It's been shifted over here, so it becomes a negative. We have to subtract it from both sides. And the c is simply m. There's nothing else has changed here. It's just what we call these things. And as I said, I've just done this because it's the standard form used for explaining this equation, whereas this is more common when explaining just the straight line here. So this equation describes this line between two nodes, between 2 points, where we've got x1, y1 down here and x2, y2 up there. How do we work out what these are? Well, k is simply the slope of this line. How steep is this? And that we can work out by calculating the difference in y. How much does y change over this change in x here? So here's the change in x, that distance there, and here's the change in y there. And put that on, so the change in y over the change in x gives us k. Once we have k is true along the whole of the line. We can then rearrange this again so that it looks like this, and work out what m is. We just pick a value of x that we know already, say this one down here, and we put that into, we have the value of x and the value of y, we put those into this formula here, along with our k that we've just worked out, and that will give us m. And m is the point at which this line crosses the y-axis. This y-axis is drawn in a little incorrectly, perhaps. So that gives us that formula. So with the help of this, we can then calculate this distance, the buffer distance, as it were. This is the distance from an object out to the buffer. So using this formula here, we can calculate this distance and therefore calculate all of the points around this line to make our buffer. Or the other way around, we can calculate that line which goes around the point. So that requires this formulation up here of that point that we're interested in, divided by the square root of a plus b. So these constants there squared. And that gives us d. So alternatively, if we know what d is to be, we can then calculate what these should be. We can turn the equation around. And this is just a quick example. I think you guys can run through this yourself. There's not much point in me going through it in too much detail, but here we can see that the calculation of k here, that's the difference in the x. 7 is there, minus 1, which is from there, divided by 9, which is the y-coordinate of that one, minus 1, which is the y-coordinate of that one. That gives us our k calculation, and then m is simply worked out by putting that calculation of k into there, and then we want the coordinates for y and x from a point, and I took this is the simplest one, 1 and 1 there. So they're in there, and that gives us the calculation of m. And then we can use the information, we then rename m and k to be the c and a up there. And that means we can then start working on this. And this then allows us to calculate that distance there, which it should be 2. Fairly straightforward. Of course, the computer is going to do this for you, but this is just an illustration of how it is done. It's not magic, it's mathematics. Fairly basic mathematics as well, nothing very advanced here. But this calculation is performed many times over in order to create our buffer. So it's quite handy that the computer knows how to do this, because then you don't have to do it thousands of times. It does it like that. Having said that, you can see that this calculation has to be performed many times in order to, if we want to buffer out this line, we've got to do this all the way around, do this calculation many times over. And that means that we need to be a little bit careful. The operation of buffering can take a little time on computers if you have many objects, especially when objects start overlapping. The computer can get somewhat confused. Not confused, it doesn't get confused, but it gets overworked and needs to start doing memory swapping and stuff like this. It can get quite heavy just because it's doing a simple calculation over and over and over again on many objects, and it needs to start working with its memory.